Hello everyone, I'm Mrs. Aparna from Modern College of Engineering. Today we will be discussing in this video about two major types of power supply, that is linear power supply and switch mode power supply. Linear regulated power supply converts an AC signal into a regulated DC signal. It regulates the output voltage by dropping the excess voltage. They use linear, that is non-switching techniques to regulate the output voltage. Here is the block diagram of the linear regulated power supply. This is the input, that is single phase 230 volt AC signal, which is given to the step down transformer to step down the value of the signal. Suppose we have a 9 volt transformer, then we convert 230 volt AC signal to 9 volt AC signal, which is given to the rectifier. The rectifier converts an AC signal into a pulsating DC signal. We have many types of rectifiers, that is half wave rectifier or full wave rectifier or bridge rectifier. Generally, a bridge rectifier is more preferred. The pulsating DC signal is given to the filter, which removes the ripples, and we get unregulated DC voltage at the output of the filter. This signal is given to the voltage regulator. There are either fixed voltage regulators or adjustable voltage regulators, which converts unregulated DC voltage to regulated DC voltage. So, linear regulated power supply converts AC signal into a regulated DC voltage. So, here we have the reflection spot. In this, we will be asking you a question and we'll pause for a while. You have to think over the answer. After the pause, we'll come back to the answer. So, the question is, which type of rectifier is mostly used in power supply? We pause for a while. Yes. So we use bridge rectifier in a power supply. The next is switch mode power supply, also known as SMPS. It converts an AC signal to a regulated DC signal or a DC voltage to a regulated DC voltage. SMPS uses elements like inductors and capacitors. SMPS employs a control circuit to manage the switching of the transistor. It reduces the need of heat sink. So we have the basic switch mode power supply diagram, the block diagram. Over here, the transistor is used as an electronic switch, which is used either in saturation or in cutoff. It is a high frequency switch. So the advantage of using a high frequency switch is the size and the weight of the component in the electronic switch reduces. Over here, we have the Vn unregulated DC voltage given to the switch and PWM, that is pulse width modulation generator, which generates rectangular pulses to the electronic switch. So, the PWM generator will generate rectangular pulse. When the pulse is high, then input, that is unregulated DC voltage, is given to the filter because the transistor will be in saturation, the transistor will be on, and the input is given to the filter. When the pulse is off, the transistor is off. So we have the input of the filter, that is the rectangular wave. Over here there are two waveforms. In the first one, we have T on period and T off period. The T on and T off period are of same value. So the average DC voltage is in the middle, this is the output of the filter, that is the average DC voltage. Now if we want to increase the average DC voltage, then we'll have to increase the T-on period. The T-on period is increased with the help of the PWM generator, which will increase the value of the T-on, and it is given to the input of the filter. So the output of the filter will give regulated DC voltage which is increased. So over here we have output voltage is equal to duty cycle into Vin. Duty cycle is equal to T-on upon T-on plus T-off. So the output voltage depends on the duty cycle and the input voltage. Next we have the detailed switch mode power supply. In this diagram, there is no PWM generator as in the previous block diagram we had seen. The input is unregulated DC voltage. But for instance, if we have to convert an AC signal into a regulated DC signal, then as we had seen in the linear regulated power supply, the AC signal is converted into an unregulated DC signal with the help of a transformer, a rectifier and a filter. So the unregulated DC signal obtained is given here to the transistor. The transistor output is given to the filter. The filter has regulated output voltage which is fed back, that is VF is the feedback signal, is given to the positive or non-inverting terminal of the error amplifier. Over here we have the voltage reference which is given to the inverting terminal of the error amplifier. Here the feedback signal, that is VF, is equal to R2 upon R1 plus R2 into VO. So the feedback signal depends on the resistors as well as the output voltage. This signal is fed back to the non-inverting terminal of the comparator. The output, that is DC voltage proportional to error, is given to the inverting terminal of the comparator. The triangular wave is generated and given to the non-inverting terminal of the comparator. So we'll see the waveforms. So this is the triangular waveform and this is the DC voltage. These two waveforms are given to the transistor. So if the triangular waveform is greater than the DC voltage, then the comparator output is positive, and if the triangular waveform is less than the DC voltage, then the comparator output is minimum. So we have the comparator output, that is T-on and T-off, a rectangular pulse which is given to the transistor. See here you can see the comparator output is given to the transistor. So the transistor will remain on for this period and it will remain off for this particular period. The transistor output is given to the filter input. So we have the the rectangular waveform, that is the filter input, and the filter removes the ripples and we get a regulated average DC voltage. So this is the output of the filter, the regulated DC voltage. So depending on the T-on and T-off period, we will get the average DC output voltage. Now if we have the output voltage is less than the required voltage, then if VO is less than the required voltage, then VF, which is equal to R2 upon R1 times R2 upon R1 plus R2 times VO. So if VO is less, then VF will also be less, which is given to the non-inverting terminal of the comparator. the reference is given to the inverting terminal of the comparator, and we are given if lower value is given to the, we are getting a lower value of the DC signal. So if VF is low, then the DC voltage is also low, which is given to the inverting terminal of the comparator. If this is low, then the triangular wave and the DC voltage, if you compare here in the waveforms, if the DC voltage is lower than the triangular waveform, then obviously the T-on period is going to be greater. If T-on period is greater than the T-off period, the average DC voltage will definitely increase. So if VO was earlier, as we had discussed, if VO was greater, if VO was less, then VF was also less, and DC voltage will also reduce, making the T-on period high and thus increasing the average DC voltage. So there is regulation taking place. So this is the basic working of SMPS. We have a question for you in the reflection spot, that is, if the output voltage is more than the required voltage, then how does the regulation take place? We'll take a pause and then come back to the answer. So if VO is greater than the required voltage, we'll just get back to the block diagram. If VO is greater than the required voltage, obviously VF will also increase. As VF is increasing, DC voltage is also more, and here if we compare in the waveforms, if DC voltage is increased here, if we increase the DC voltage, then what will happen? The T-on period reduces. The T-on period reduces and automatically the average DC voltage will reduce. So this regulation takes place. Next is the applications of SMPS. SMPS is generally used in computer power supplies, in mobile phone chargers, in telecom systems, and also in the servers. We have the comparison of linear power supply and SMPS. Operating region of the switch is the linear region for LRPS and is the saturation region for SMPS. Semiconductors used is normally BJT for LRPS and BJT or MOSFET for SMPS. Efficiency is up to 60% for LRPS and it's very high, up to 95% for SMPS. So the efficiency is good for SMPS. The conduction losses are high for LRPS and they are low for SMPS. The circuit complexity, now here the circuit is less complex for LRPS, whereas it is much complex for SMPS. Operating frequency for LRPS is 0. For SMPS it is 10 kHz to 1.5 MHz. There is less noise and interference in LRPS compared to SMPS, which has high noise and interference. Regarding the size and the weight, it is more because of the transformer, whereas SMPS is less, the size and the weight is less for SMPS. Applications: LRPS is used in simple low power communication and control equipments, and in SMPS it is used in complex high power office equipments and small appliances. So this is the comparison of LRPS and SMPS. These are the references provided. I hope you liked the video. Thank you.